Okay, nice to meet you, everyone. Um, so this is multivariable calculus class, and my name is Hyosang Kang, and you probably have the syllabus, but I'm going to go through the syllabus today, and because we have a major change in our grading scheme. So first, in the beginning of when I wrote this syllabus, I didn't intend it to have a serious project-based learning, although I intended to have some, but um, during the vacation, I applied for a project-based learning program, and then they selected me, so I have to run this class as a serious project-based learning, and some of you guys like it or some of you guys don't like it. So I just make clear and what we're going to do in this class. And if you don't like it, I know that this week is also you can change your course registration. So please do make a change before you cannot do so. All right. So before I start, I'm gonna call out your names. So everyone to check everyone is here. Can I borrow a pencil or a pen? Oh, yeah. So there are many people. So if I call your name, please answer with verbally. 강민지, 강민지. Yes. Please say anything so I can hear you. 고은서, 고재원, 공준영, 공준영, 김규, 김규린, 김다인, 김동훈, 김동훈, 김민성, 김승윤, 김윤서, 김정현, 김주효, 김현수, 예. 김형환, 도한수, 민용기, 예. 박성현, 박윤동, 예. 배주영, 송민준, 신은우, 네. 심지원, where? Yes. 안재민, 안현수, 안혜정, 양원빈, 온가은, 네. 유승헌, 윤하경, 이성준, 이시환, where? 네. 이영호, 이준우, 예. 이지유, 이채현, 이편주, 이한진, 임유빈, 전종일, 전지민, 정헌규, 예. 재혜준, 조용준, 조환진, 지태현, 진서연, 최규범, 최보성, 최수원, 예. 최정훈, 한승현, 허윤지, 홍선민, 황교찬, 황연지, 황인재. Okay, so last three people, if I pronounce your name incorrectly, please correct me after class. Mushfik. Okay, Mushfik. Okay, Sandram. Okay, Sannur. Okay, thank you. Is there anyone who I didn't call your name? Raise your hand if I didn't call your name. So anyone who haven't registered this class but still here? Haven't registered class? Raise your hand if you haven't registered. Not registered? Oh, okay. So I'm not registered. Just two person? Okay. No more? All right. So you can meet me after class, although I probably sent you an email, right? Yeah. After class, let's talk. All right. So syllabus. Let's talk about the syllabus. It's a major change. All right, so here, the most important part is grading, right? So we had midterm, final, quizzes, and projects. So midterm was 25% before. So it's going to be 30%, not that different. So 25% of final will be 30% of the grade. And so quiz was 20%, and let's not have a quiz, so it's going to be 0%. And project was 20%, it's going to be 30%. Okay? So already the project was 10% each. There were going to be 2 projects, the same number of projects we have, but it's going to be 15% each. And there was one more, tendency. So 10%, still 10%. So 30, 30, 30, and 10. Okay, so this 30 is going to be 15% each. And for the project 1 and for the project 2. All right. So if anyone not satisfied with grading scheme, then you can, you can change it to other section if you want to. And I think I haven't explained detail about the project 1 and 2. So here is more detail. So everyone clear about this grading scheme? No questions? Because I'm going to erase it. Right? So what we're going to do in the project 1, so let me write down the objective here. So you're going to add your original idea, 1 or 2, to one of the following project topics. So I'll call it toy project. So these toy projects, there are 9 of them. I'll just list the topics here, and I'll show you how to find out the detail. So first of all is making a calculator. And the second one is making a CAPTCHA. And third one is drawing a contour. And fourth one is simulating a spring oscillation. And the fifth one is simulating heat map. And sixth one is image processing. And seventh one, basically sixth one is the AI, machine learning. The seventh one is Cauchy-Crofton formula. Let me write 8 and 9 here. 8th one is area of polygon. And 9th one is magnetic dipole. Okay, so you have to choose one of them. You can choose actually two. You can mix them together if you want, if you can. At least you have to choose one. And all these projects are going to be introduced during the class. And you can also look up the content of the project in this book. So in the syllabus also, I mentioned that there is a textbook in this class. So this is the, sorry, this is a Korean though. It's a book that I wrote last year. I'm going to use this book throughout this class. And the content that I'm missing in the class, because I cannot cover the entire content, is going to be in this textbook. I'm not saying this is the perfect book, but it's going to be the guide, what we're going to cover, and what's inside the content, which I didn't cover in the class. Although if I talk, then I can certainly cover more, but some facts can be delivered in the writing better than talking. So anyway, so I think you can get this book anywhere in the online store, and I found that the library haven't got this book, haven't get this book yet. I'm not sure whether you're going to get it or not. But anyway, so if you want to see this book after class, I'll happy to show you what it looked like. And yes, question? Is there any, like, other books that covers the same topics but in English? No. Because I don't understand. Yeah, so sorry for that, but we are going to, yeah. So, is it crucial to have this? Like, well, not crucial. Well, of course you can. Well, of course, all the material that we covered in the class will be on the exam. Okay, no quiz, and also projects. I'm going to cover it in the class too. So, yeah, well, if I don't recommend, if you're not native Korean, to buy this book unless you want to study Korean personally. But you can still, say, borrow this book if you can, and find some translating app to find out what the content is about. And also, you can, if you pay attention to the class, you can certainly get more than what I wrote in the book, because some book in the content still there's some point that I didn't make it clear. So if you, I mean, I don't recommend rely heavily on the book or heavily on the classroom. You have to do both. But I know that some people always have a complaint when I introduce these topics, that they want the code, they want some what is going on, and the book tries to explain what this is about, and it has all the codes that you need. So yeah, that was my concern when I'm writing this book in Korean, but the publisher wanted Korean because that covers more audience. So yeah, sorry for that, but yeah, so if you have any trouble, I'll make it as minimum as possible. All right, so and also, these topics are listed in sequel. So these 4 or 5 topics are covered in the first half of our semester, and 5 to 9 will be covered in the second half after midterm. And the first part is about the differentiation and also some basic stuff about function. And the later part is about integration. So if you want to cover the later part topics, like magnetic dipole, you kind of wait until the end of the semester. So if you really want to do the later part topics here in project 1, you can give it a go after you do the project 2. So the project 1 and 2 are different topics, different. It has a different objective. So if you want to do the project 9, for example, in the project 1, then you can do the project 2 first, and then do the project 1 later. Okay, so is any question about the project 1? Well, probably a lot of questions, but just ask any if you want to. So the project is in groups. It's not an individual project. You have to form a group, and it's a group of 3. And I'll let you find your group first. If you can't find your group, I'll just randomly assign the group. But I recommend you to find as close friends as possible. So that's going to be better for you to spend the rest of the semester with the good friends, not any random friends that you don't know. Yes, 3. Yes, more 3 or 4. Yes, but 2 is not recommended. 2 is too small. The same group for the both projects? Yes, I recommend keep the same group. But okay, so the advice that I got after I applied this project-based learning program, the advisor, the expert in the education recommended me to make a bigger group for the second project. But the best is having the same group for both projects, and also have a group with 3 people is the ideal. But if you want to change, you can change, certainly. All right, so any other questions? Yes. Yeah, everyone get the same grade for each topic, for each project. So yes, the good point. I haven't mentioned about the grading scheme. So project 1, so there are grading schemes are different. I think I should put that in the LMS after this class. It's kind of complicated. So let me clarify the grading scheme. So the project 1 will be mostly about mathematical accuracy. So that's going to be 40% of your grade. So it's a 40% of 15% of the total grade. Okay, so that's not much. Okay, and programming. So by the way, all these topics involves Python programming. So you need to produce a code in Python language to do these projects. So you have your program, your code has to work. So that's the programming part, and also consistent with your ideas, what you're going to accomplish. And the creativity, creativity, that's going to be 20%. So the main theme is not doing the same exact toy project as I did in the class. You have to add your original idea, 1 or 2. So that's this part. And the last one is presentation. That's also 20%. So you're going to have a presentation. You don't need to submit your report. You have to present it in the class. I'm thinking about the format still, because there are so many people. If I divide it into group of 3, it's going to be almost 20 groups. So I'm not sure whether I can let 20 groups to present your work in one class. So I'm still thinking whether I should have a presentation or the poster session. But we'll see how it goes. So I think it depends on how deep your project is going to be and how you're involved. So if you need more time, maybe if you need a lot of deep knowledge or deep understanding or deep research involved in your project, maybe the poster session is better. But if you really want to, be more creative in your presentation, I'll let you present in front of our class. So we'll see how you guys, how your characteristic, you guys characteristics are. So all right, so that's basically the scheme, the grading scheme of project 1. Any questions? No? Okay. Thank you. All right, so project 2, I want to be clear again, because it's not listed in the syllabus, you to understand what we're going to do in this class. And mostly, what I emphasize the most is not the content of mathematical stuff. It's actually what you do in the class as a project. The second project is design research project. So it's a project that designing a project. So which aims for Ig Nobel Prize. And well, not just random Ig Nobel Prize. I don't want you to have an experiment in physics to have an Ig Nobel Prize. I want you to have a mathematical modeling involved in this project and uses. So when I say mathematical modeling, it means just you have to use some kind of function to model your problem. So it could be a physics problem, it could be a chemistry problem, whatever you want, but I don't want you to be like abstract thinking project, like a philosophical problem or some theory in humanistic. Rather, I want you to have a real life problem that makes everyone be more creative and have more interest in our neighbors, and also make everyone laugh when you present something like this. And I rather not give any example of this project because it will, it will hinder your creativity. So if you really want to, you can look up Google or ask ChatGPT what was the uh, mathematical Ig Nobel Prize project in the past, and you will see there are lots of weird project or weird research, but it was really a research, and he got the Ig Nobel Prize. So it's about ideas. So let me show you. Let me write down the grading scheme. It's a bit different from the first project. So the creativity is the 40%. That's the most important part. Okay. And you also need the mathematical accuracy. So it has to make sense. You're not making a novel here, so accuracy. So that's 30%. And presentation covers 20%, the same. So there's no programming part. So you don't really need the programming, but if you need to, you can put the programming, and that's going to be covered in this part, mathematical accuracy, to support your idea. There's another part, it's called peer review. So that's not in the project 1, but I included peer review in the second part because it's really about communicating that stresses on the project 2. So you have to communicate. You have to think about how to deliver your idea. Why is it important? How you did it? What is your goal to your audience, which is your student, your mates, and that's going to be reflected in the last component, peer review. So I'll ask everyone to assess other people's project 2 topics, and then I collect all the results and then reflect it on the grade. The only small portion, 10% of 15%. So you don't have to worry that much about that part. And yeah, usually the project is just for your understanding and it's basically for your fun, not making you suffer. So anyone who took my course in the last semester or last year will see that the project is the part that is really hard to differentiate students. So I don't tend to differentiate your uh, your your performance by the projects. So I want to just encourage you to finish the project and get all the full marks on every aspect here. Because how do I, like, how do I judge the creativity? Let's say I have 40%. How do I make a objective creativity in numbers? Well, it's kind of impossible, but you'll see it's kind of it's kind of bureaucratic in some sense, right? So, anyway, so that's the main difference from the syllabus. Any questions? Yes. About project 2, so at the end we need to write kind of paper. Yes. Oh, you have also the final product is presentation. Not paper. Yeah, they don't have to write the paper. I mean, encouraged to write the paper if you want to. Okay. Yeah, yeah, basically. Just the presentation. Any other questions? No. Anyone else? No? Okay, 1, 2. All right. Okay, so we're gonna have a class today. Some professors don't have class on the first day, but we have lots of materials to cover. I generally start with the title of our subject. So what is our title of our class? What is the name of our class? It's a multivariable calculus, right? So we need to understand what the multivariable calculus is. So by the way, I am recording the lecture every time. So I'm going to upload it on my channel, and I'm going to put the link on the LMS. So if you want to rewatch the lecture, you can always do after class. So, okay, so multivariable calculus. So it's a two-syllable word, the multivariable and calculus. So what is calculus? Calculus, basically, it's calculating. What do we calculate? Yes, differentiation and integration. That's a basic way of calculating things. And it's actually not all the ways, but differing. So why do we need differentiation in calculating things? Why do you think we need differentiation? I think no one ever talk about why we need differentiation and integration when we talk about calculus. If you look up the calculus book, there are lots of skills and lots of problems and examples, but they never touches the heart of why we need differentiation. So you'll see, I mean, I'm spoiling you again, because if I let you ask at the end of semester, well, everything will just make sense, but it's really need to know that in the beginning, what are we doing? So differentiation is basically making everything linear. So what is the simplest function, but still important function? But So the most simplest, just if you think about the simplicity, is the simplest function is the constant function, right? It's like a zero function. But that doesn't have any meaning. I mean, it's not really important to know what it's about, constant function, which is less simple but more significant is the linear function. So this differentiation is make everything linear. That's the idea. Why do we have to make it linear? Because our mind, human mind, wants the simple thing. If we understand the simple thing, and if we make everything simple, we can understand it better. Linear function is the most simple thing. Linear means just a line, just the straight lines. Everyone understands what the straight line is, but if you get to the curve, then there are lots of things to think about. There are curvatures, there are ways to curve it, the direction, and so on. But linear is just simple, so simple that if you can make everything linear, then you can model everything in the simplest way. So that's the idea of differentiation. What about integration? Why do we care about the integration? What do you do with the integration? Well, if you have learned about integration in high school, what did you do with the integration?
Basically summation of small parts
Yes.
to calculate the area under curve.
Right. What's your name? Sorry.
Syndrome.
Syndrome. Sundrum. Yeah, Sundrum. He mentioned the important keyword, the area. Okay, so it's basically chopping off into small pieces and then sum them up for what? You want to calculate area, volume, or sometimes length. So you do something with the geometry. Right? So of course everything is not linear, although differentiation tries to make everything linear by approximation. But if you really want to understand the real world, it's not always linear. So you need to evaluate non-linear thing. For example, how do you get the area of a circle? Well, you know the formula pi r square, but where does it came from? It came from the integration, basically the same idea of integration. So unless everything is rectangular, you need the idea of integration to evaluate the property of the geometry. So property could be area, volume, whatever, or it could be also some other stuff that you need in other studies. So these are main focus of the calculation. So calculus. So that's why we call it calculus. Calculate things. So you can summarize these two ideas as something like you want to understand your reality. You want to understand your surrounding, your environment by mathematical modeling. By sometimes make it linear, which is the simplest object you can think of, by sometimes using geometrical object, and basically you want to understand the surrounding. That's the basic idea. That's why we always start with the calculus whenever you go to university. Everyone learns about the calculus, even even who wants to major in humanities. They need to know what calculus is talk about because that enlarges their understanding to our neighbors and universe. So now we're not just talking about the calculus. We have a multivariable calculus. What does multivariable means? That means basically there are many variables, right? Multivariable, not just single variable, several variables. What is variables? What is the variable? What are the variables? What's the meaning of variables? Yes, so it's uh, something that's not constant, right? So it's let's say parameter, a different name of the variable, parameter, and not constant. And why do you need the parameter? Why do you need the variables? Why do you need them? Why does function? So basically, variable is for function. Why do you need variables in function? To find what? Yes, to find the dependencies and relationship between the variables. And also that comprises to modeling of our situations, right? So finding out the relationship between variables and the outcomes of one variable to another is basically increases our understanding of the model that we are thinking of. So it's really about modeling. So modeling is not real situation, but it's a mimic of the real situation. When you model something, sometimes there are only one parameter to consider, but almost never you have only one parameter to think about. So now when you think about the multivariable modeling, you get to the real stuff. You get to the real simulation of the nature and environment. So it's a modeling of real situation. Now, mathematically, we want to understand how to do it or some methods or techniques. So in real life, there are thousands of variables required. For example, if you think about machine learning, AI or ChatGPT, something like that, then they have trillions of variables inside. So computer can handle it, that's why. But what we're going to learn about in this class is not how to deal with those tremendous number of variables. We only need to know how to increase our idea of calculus of single variable to two variables and three variables. If you can increase, if you can jump from one variable to two or three, you can enlarge it infinitely because all the rest of the ideas are almost similar. So just get from one variable situation to two variable situation is quite different. So um, it shouldn't be different because generally they're the same thing, but if you learn about the single variable calculus, or if you took the course in engineering mathematics 1, they always talk about the single variable case. And in the single variable case, people have make it reduced all the theory down to earth that only works on single variable case and make it easier to understand. So that's why it's sometimes different in the situation where you have a one variable and two variables. So in this class, we're going to have a universal theory that works for one variable and two variable and three variable and thousands and millions, trillions of variables and so on. So that's what we're going to talk about throughout this class. All right, so that's basically overview of our material, our subject. Any question before we begin with our first topic? Any questions? No? Okay. Okay, so let's talk about sequence. Um, so if you find your textbook, I try to make it self-contained, but usually the multivariable calculus textbooks start from not from the sequence, but from some differentiation of two variable functions and so on. But um, in our DGIST curriculum, we have single variable calculus course, but it's not mandatory, so almost no one takes that course. So I feel like I have to start from beginning or start from the bottom down to earth when I talk about the multivariable calculus. So that's where I start. I need to talk about sequence. So what is a sequence? So let me define a sequence. I'm not going to make a rigorous definition. If you're more like I'm a mathematical guy, then my definition may not feel right, but I make it more commonsensical so that everyone could understand as at least intuitively. So a sequence is just a list of numbers. Okay? So that's as far, I mean, at least the way I defined a sequence. By the way, sequence could be a sequence list of functions. It could be a list of matrix. It could be a list of other objects. But we don't use that kind of sequence in this class. So every sequence is a list of numbers. So how do you describe a sequence? So there are three ways. To describe a sequence. So you need to be able to define what sequence is. So the first way is just listing numbers. You can just list a number like 1 minus 1 over 4, 1 over 9, 1 over 9, and minus 1 over 16. And you could have a finite sequence if you stop there, but if you want to have an infinite sequence that the list goes on and on forever, then usually you put dot, dot, dot here so that the reader or anyone could guess what the next one is. So what do you guess the next sequence is? After 1 minus 1 over 16, what do you guess? What comes next? After minus 1 over 16? Yes, 25. Yeah, so you can, yeah, so on. Of course, who knows? I didn't intend it to have 1 over 25. Instead, I get 0. That's what I intended. But that's not the right way of using this method. So when you're using the listing method like this, then you kind of imply that there is a pattern in your listing, and the pattern is apparent to anyone who watches. And then if it's not apparent, then you shouldn't use the listing method, right? So another way of describing sequence is by words or formulas. So formulas is just a different way of putting it in words. So if you can put it in a formula, you have to be able to write in words or sentences. So for example, AN. So I didn't mention the notation, but let's say AN is the nth prime where A1 is 2. So here AN denotes it's the nth number in the sequence, and I define that AN is the nth prime, where the first entry of the sequence is 2. So 2 is the first prime, the smallest prime, right? So when I say this, then I order the prime in number and in sizes. So when I say A2, then it's going to be 3. A4, it's going to be 5. A3, it's going to be 5, and so on. And what's the next one? You can also describe a sequence with recurrence relation. So the best example is the Fibonacci number, an plus 2, an plus 1, an, where when you have a recurrence relation, you need to have a starting point. Here, the elements in the sequence always depend on the previous two sequence number. So you need to provide the first two entries in the sequence in order to find the next one. So let's say usually we define first two elements in the sequence of Fibonacci number as 1. So in that case, you can use this recurrence relation where n is from 1, that you can find A3, which is A2 plus 1, A1, and A4 as A3 plus A2, and so on. You can go on. So this is sufficient to define every sequence element in any entry, right? Because it goes inductively. So the mathematics define, or mathematical logic has several tools to make mathematics logical. One of them is inductive method. So if you define some element is dependent on the previous element you find, then you can keep doing it until you can find whatever you want. So here, it is sufficient to have this relation with the first two numbers, that if you take any natural number, you can always compute inductively by lowering its index of the sequence, right? So let's say if you have 1,000 here, you can still break it down into 999 plus 998 and so on. You can go on forever. I mean, not forever. Finite steps, and then find what that is. All right. Well, what I want to, what I usually do in the previous semester and also in this class is I want to have a Python program used actively to understand the mathematical stuff. So I need to, let's see. So I try to use my computer, but the project doesn't show my screen, so I need to use this computer. Let's see, I think I have to log in. Oh, okay, so maybe I can use Colab without logging in. So let's see. That's good. No. Yes, new one. Oh. Okay, so I have to log in anyway. Can I? Maybe I can just. All right. Okay, maybe I can just use this code block. So let's try to define our sequence in Python language. So just for my information, if raise your hand if you have any experience in Python language. If you don't have any experience in Python language, don't. If you don't have any experience. Okay, so everyone, you have? You are in my class. Okay, yes. Okay, so at least everyone has at least some experience. Okay, you know what the Python program is. So it's just maybe it could be just a review. Okay, so all right, so okay, so let's say I have finite sequence. So how do you define a finite sequence? Well, it's just the finite entries are there, so I can use the list in the Python language to define a finite sequence. For example, 1 minus 1 over 4, 1 over 9, and minus 1 over 16. So that's just a sequence of 4 entry. But, okay, so how about, okay, so I have to log in anyway. So that's me. Okay, let's log in. Okay. If it's too small, I can increase the size. I can zoom in more. Is it small? Can you guys see the letters here? Person in the no? How about this? Okay. So let's define a sequence, infinite sequence. Uh, the first example. How do you define this infinite sequence? So you want basically sequence is something that gives a number when you input an entry. So if you want to find out the 10th entry, you put into a function 10 and you get some answer, which is the A10, right? So you need to define a function with the inputs, which is int type, and let's put a float type as an output. Okay, so usually you probably have no custom of putting this column here with the type of the entry here, but I like to put this way because it shows me what the data type should be. And okay, so int type has a negative number. It could also be 0, but in our case, in our class, we tend not to have zeros entry of the sequence. We always assume that the entries start from 1. So if n is less than or equal to 0, then the input is wrong. It shouldn't have any entry in index less than or equal to 0. So I'm going to return none. Okay, so none is not a number. So if its n is not 0, what happens? So I need to find a pattern. So this is A1, this is A2, and this is A3. What's the pattern here? There are two patterns. Which one is the sign? Sign changes from positive minus, and the denominator increases with square, right? So depending on the parity of n, so if, so let's say, so if n divided by 2 has remainder 0, that means I have even entry, which has to be minus of something. So get the return of minus of what? 1 over n square, right? So if it's 1, so if the remainder of after dividing by 2 of n is 1, then it's either 0, but in other case, it's always 1. So it has to return positive number, has to return 1 over n square, right? So let's check. So that's my definition of the sequence, which as a function of the Python function. So let's print out A1. Oh, it's just 1. And how about 2? 1 over 4 minus 1 over 4. Let's print out several of them. Let's say 10 of them. So I'm going to print out the list of entries. So here's the list. Oh, actually, it goes above our box here, but you can see what's happening. So we have a loop mix with a for command here. So I goes from range 1 to 11. So whenever you have a Python range function, it goes from this number to the one less than the second number. So it's 1 to 10, not 1 to 11. So this I never gets to 11. It's just 1 to 10. So it covers 10 first elements. And then you put that I into the function A, and then you get the result. So you see that it's in the decimals, but that matches with the numbers right down there. Okay. So how about the second one? So we have the sequence defined as that an is the nth prime. You don't have a formula for that number. And there's no formula. There should be no formula. If you find the formula, you're a Nobel Prize. So how do we find how do we write down that function in our function, the Python function? So same thing with input number and int, but now the output is also int. So let's specify that the output is int by this way. And let's see. So I start from prime 2 because that's the first prime. I know that. I need to know that. How do you go from there? So if n is 1, then I can just return 2, which is the last entry of this prime variable. And this prime variable is the list of numbers that I'm going to put all the primes in SQL. So for I in the range, but I didn't really need I here, n minus 1, because here again, I need to have an exception here. If n is less than or equal to 0, then it doesn't make sense, because what is the zeroth prime? What's the minus one's prime? It doesn't make sense. So in that case, just let's say return 0. You can make it panicking, but I just make it return 0. And I only want to run this situation for at least n times. So if n is 1, then n minus 1 times, sorry. So when n is 1, I don't want this loop goes on because I already have the first entry already here. I want to just return that entry, return prime minus 1. Okay, so the red dot, this curly red here is because I didn't have any content after the loop 4 here. But anyway, so that's the basic, structure of my definition of function A. And what I'm going to do here is, okay, so I'm going to increase my number. Let's say, I'm going to start from prime, the latest prime, the last prime I found, plus 1. Okay, so in the first for loop, I start from 3 because the last prime I found is 2 because it's already given. And I start from 3. And what I do is checking whether the previous primes divide the next number. So so I'm going to is prime. So I'm going to check whether the number m is going to be prime or not. And let's see. Is prime is true first? Oh, not 4, sorry. So I'm going to have an infinite loop until I find one. So if all the p in the prime, if p, so m divided by p equals to 0, then is prime is false. It's not a prime. So I'm sorry. So I have to loop and whenever it's not a prime. So whenever m is not a prime, then I'll go forever until I get one. So first, it's not a prime, false. But let's assume that it's prime in the beginning. But then if I go through all the primes that I found in previous times, and if some prime divides my number, then it's not a prime. So I have to change my variable is prime as false. So then whenever then that is done, I don't have to look for another prime to divide it, just to go outside of the for loop. And then because is prime is make it into false, then it's not going to pass this while. So it's going to pass this while and then move on. So if it's false, so it happens this once, then I have to increase. So and then, yeah, I think it's done. So when it's done here, so if p, if the m is prime, if is prime, true, then what do? We found the prime, right? We actually found the prime. The m is the prime that we didn't find yet. So we need to add that prime into the list of primes here. So prime append m. So that means my list is increased by 1. So I'm doing it for how many times? N minus 1 times. So the last one is the nth prime. So let's put it here. So that's my sequence. So basically, I had an algorithm to find the nth prime. So let's check whether it's doing right. So most of the times, if you write the algorithm for the first time, it never works. So you have to check again whether it works. Let's let's print the first 5 primes. Yeah, that looks right. 2, 3, 5, 7, 11. How about we increase a bit more to 10 primes? 11, 13, 17, 19, 21, 23, 29. Yeah, it seems right. Yeah, so it works. So I'm showing you how to find the sequence if it's given as words or formulas. So if it's given as a formula, it's straightforward. Everyone knows how to write down the formula, but it's when you have a verbal description of a sequence, you need to think about how to compute it. So sometimes it's very interesting that sometimes mathematicians come up with a verbal description of an object, and sometimes it turns out that object doesn't exist. It's a contradictory statement that to say that this object is the object is really there. So you need to be really careful when you define some objects here. So in this case, it's quite obvious, but I'm saying that unless you try out by yourself, you don't know whether it's really existing or not. So how about the last one? So recurrence relation. I also want to define a Fibonacci number like this. So let's use the Python definition here. And also, the output is the integer. So here we need to keep the latest 2 entry of the sequence, right? We don't need the entire sequence. Of course you can, but you can keep all the sequence, but it doesn't really need to. So my m is going to be just 1 and 1, which is the first 2 entry of the Fibonacci sequence. And what I do is, okay, so if n, okay, again, so this is the entry, the index is less than or equal to 0, then I return 0, which means nothing, because it's not valid entry. And otherwise, then I get, so there are 2 cases, in other case. So either n is less than or equal to 2 or bigger than 2. So when it's less than or equal to 2, the entry of that sequence is already here. It's A1 and A2. I just return accordingly. So here, it's always 1. So n minus 1. So if n is 2, I need to return the later one. And when n is 1, I need to return the first one. Okay, so maybe sorry, confused with the other language. So okay, so therefore, I had to input n minus 1. So in the Python and many other computer language, the index start from 0, not from 1. The index from 0. So although in the mathematics, we define the entry of the sequence always start from 1, the index 1. In the computer language, index always start from 0. So this is M0, this is M1. So when n is 1, I need to go for M0. That's why I need to take 1 off from n. And when n is 2, I need to go for m1, so that's why I need to take off 1. So that's the case. And then how about rest of the case? Else what? So I need to iterate so that I get the appropriate entry, right? For something in range. So I'm just make a variation in my coding so that you can have a lots of different way of coding things. So here I didn't put any variable before the command in. So when you have a variable, you can use that variable, the value in that variable inside of the loop. But here I don't need that value. So that's why I put just the underscore, just leave it as a blank. But you can just delete this because that would be not right in the syntax. So just put a blank here. And what? I'm keep updating. So I'm updating m1, mn0 plus m1. So what I'm doing here is I'm updating my list of m as the last two entry in the sequence. So if this were the first two entry, the last two entry in the first stage, the next stage is that the last two would be the second and third. So I need to move the second entry of the previous stage to the first entry here. So I just moved the location of the first entry here. I mean M1 in the M0 place. And then the M1 now is going to be the sum of the two numbers in the previous stage, to these two numbers. And I keep repeating it, keep repeating until I get the proper number. So it's going to be return the last entry. All right, let's check the result here. So if you know what the know something about the Fibonacci number, then you will see that it's going to be the right 1 to 11. Let's see. So 1, 1, yeah, that was the first two entry, and 2, which is the sum of first two, and 3, which is the sum of the last two here, and 5, 2 plus 3, 8, 3 plus 5, 13, 5 plus 8, 21, 8 plus 13, and go on. Right? So I think it's right. And the Fibonacci number increases very fast. So if you go like 21, then you can see that it goes exponentially larger and larger. All right. Just a review, but if you have any questions, let me know right now. If you have any question about the programming, yes. No? Nope, not a question. By the way, why are we talking about the representation of sequence? Because basically, sequence is a function, and whenever you're dealing with a function, you need to think about all these methods. We're going to talk about this later when we talk about the graph of a function. So describing a function has three ways too. You can also describe a function with the values, listing the values of function in a table. Or you can also describe a function with the words or formulas. And also, well, the recurrence is a little bit different. Another way of describing a function is a graph. So you have to think about ways of describing your function, because in your project, you have to describe your mathematical model, which is also a function. So you need to define clearly what is your modeling, what is your model in your project. All right, so okay, so another question. So far we covered what is a sequence, and let's talk about different aspects of sequence. What does it mean by that the sequence is converging. What do you mean by convergence? What do you mean by converging? So before we talk about the definition, let's draw some graph. Let's draw the graph of a sequence. So the sequence is given by the recurrence relation. an plus 1 equals 1 over 2 an plus 2 over an. And this an start with a1 is 1. Okay. Okay, so we can draw by hand, but it's wiser to draw by program because Python is such a powerful method. We can easily draw the graph. So first, we have to define that function, the sequence. Let's say n. So input is an index, int, and output could be float. So it's float. So again, I want entry start from 1 when n is 1. So if n is less than or equal to 0, then I'm going to return none, which is not a number. And then iterate. So m is going to be the variable that contains the latest entry of the sequence, and it was 1 in the beginning, but I'm going to iterate how many times? Iterate n minus 1 times, because when the first entry is already covered, it's defined as 1. So if I'm asking n equals to 1 case, then I can just return m. In that case, the range parenthesis inside parenthesis is 0 when n is equal to 1. The range 0 means that 0 to less than 0, so it's nothing. So range 0 have non-entry in the list, so this for loop doesn't work. But so only works when n is bigger than or equal to 2. So it runs n minus 1 times, and m is always replaced by 1 over 2 m plus 2 over m. So here, again, let me just review briefly about the coding here. On the right-hand side, m contains the previous value, the old value of the variables. And this equal means that it's replacing replacing the variable, the content of the variable m with the right-hand side value. So this m and then this m is not the same. I'm not talking about the equality. So it's just assignment of the value to the left-hand side. So after doing all this loop, let's return m. So so whenever you type in the code here, you have to run this code block so that the content of this code is registered in the cloud. So either you click this button or you put the shift enter or control enter. And then let's print out AI, AI for I in the range of 1 to 11. Forgot the parentheses here. Okay, so now we got the result. You can see that it actually converges to some number, 1.414. Actually, it's square root of 2. And let's draw this. So when you draw something, when you do any kind of a plotting, you have to import matplotlib, pyplot. And when you import something, usually you can go by the full name, but you can abbreviate, you can assign a new name for this because it makes simpler. I'm going to abbreviate it as PLT, and that's the conventional way of abbreviating pyplot. So when you plot something, you need a point. You need to connect the points. So you need x coordinates and y coordinates. So x coordinates is going to be just the list of natural number from 1 to 10. So let's draw the first 10 entries of the sequence. So I in the range, so I for I in range 1 to 10. And the y coordinates are the values of sequence for each entry in this list X. So I'm going to compute the AI for every I in the list X. You see, X is a list. I used it in here instead of range. So range always give the list of natural number. Well, maybe not the natural number, but if you have, unless you have a third entry here. But anyway, here also same thing. So I run through all the entries in the list of X and then compute AI and put that as an entry of Y. So here the plot X comma Y, and let's hit enter. And you can see the graph, right? So it's very interesting graph. It looks like it only have a 3 segment of line, but it really does not have 3 segment. It has a 10 segment, maybe 9 segment. But after this point, so it was 1, it was 1 in the beginning when x is 1, 1 in the beginning here. And then it goes up to 1.5, not that much, but anyway. Then the 3, you get 1.4 something, and then the rest of the part is almost not changing much from 1.414 or something. So it's converging, right? It's a nice converging sequence. So we're going to use this plotting many times when we try to understand the behavior of function or sequence or series. And our question is, what does it mean? Well, you can see that it's converging, but you want to make a statement which is true statement or provable statement about convergence. So how do we define the convergence? Okay, so here again, I'm gonna give 2 layers of different definitions, 2 layers of definition of convergence. This is the first layer, which is kind of intuitive. A sequence AN is said to be convergent So by the way, converging, convergent, convergence, they are all the same, but different grammars. But don't think about this as a different meaning, different words. Be convergent if AN approaches to a unique number L called limit. So this number L is called the limit when the index N goes infinity. Okay, that's kind of intuitive and that's not really rigorous, but I'm going to keep this definition for a while. And that makes sense, okay, right? So in this case, I didn't let n goes to infinity, but you can guess, you can easily guess even though you don't let make n to be very big, it's already stabilized in 1.4 and it's going to be stabilized forever. We guess by looking at the graph. So it matches with this definition. So we can say that this AN given by this recurrence relation is convergent. So the question is, what's the number L? What's the limit? Oh, we'll see that that's actually square root of 2, but here, let's talk about convergence a little bit more and then talk about the limit again. So another definition is that sometimes sequence is monotonic increasing or monotonic decreasing. So AN is monotonic increasing or decreasing if the entry always gets bigger That's the increasing case. And always gets smaller. That's decreasing case. Okay. All right. So another definition is n is bounded above or below. So bounded above means that there is a number which is above all of the entry of the sequence, such that an is always less than some constant m. So m is constant here. Okay, it doesn't change, doesn't depend on the entry n at index n. And if it's below, bounded below, then it means that an is always bigger than some constant number m. So here's the theorem. So we only had defined things. We need to know which sequence is convergent and which is not. So at least there is a theorem that tells us in special situation you can say the sequence is convergent. A monotonic increasing bounded above sequence is convergent. So if the sequence has two properties, one is monotonic increasing and the other is bounded above, then it's always always convergent. Okay, so how about this way? So can you use the theorem? Can you kind of apply theorem to our situation here? So it's bounded above, and it's actually bounded below, because there is certain bound, like a 0.5, 1.5. No sequence is above 1.5 level, so it's bounded above. Is it monotonic increasing? It's increasing in the first, but it's not increasing in the second. It's decreasing, right? So how about we just forget the first three or first two? Let's say I do this. Yeah, it's getting quickly converging to numbers. So let me decrease it a little bit here. So, okay. Oh, it's still decreasing so fast. Okay, so 5 here. Okay. Oh, it's actually 3 to 4. So you see, if I take the 3 to 4, the entry 3 and 4 is decreasing, and let's change it to 4 to 5, 4 to 5, 4 to 5. Then it's still decreasing, right? The amount of decreasing is very small. You can see that it's 10 to the minus 6. So very small, but still decreasing. How about 5 and 6? Still decreasing. So you can see that the sequence we just draw with the recurrence relation is always decreasing after the second entry, right? So how do you use this theorem? So you can just revert the situation. If the monotonic increasing and bounded above sequence is convergent, if you just reverse the increasing to decreasing and bounded above to bounded below, everything should be same. So just take the reflection around the x-axis. So if the increasing sequence, which is bounded above, it always has to converge, then if you flip this over, like in the negative direction, so it's positive direction. So if some sequence is decreasing but bounded below, then it always has to convergent, right? So the same thing goes on here. Sequence is always convergent, always decreasing after second entry, and it's bounded below. We know that because we draw sufficiently large number of entries in the sequence. So therefore, the sequence we just draw is convergent by the theorem. We can ignore the first few finite terms. The first few finite terms doesn't matter, doesn't affect the convergent and divergent. So if you take out the first few finite terms and then the rest of the term, which is infinite, satisfies the condition of the theorem, you can say that it's convergent. We can go for another example. Let's see. How about this one? Let me give an example here. Oh, by the way, yeah, I think it's okay. So how about an equals to 1 plus 1 over n to the power of n? Let's go for this one. Let's draw the graph of this sequence. It will be convergent slowly, a little more slower than the previous one. So an, so let me increase this a bit, and n, 2, so it's also float. So now I already have formula, right? So I don't need to code anything, just put the formula into the code. So 1 plus 1 over n to the power of n. So that's a definition. And let's draw the graph. So I'm going to use the same code here. And from 1 to 10, you can see that actually it's increasing nicely. It's not increasing too fast and too slow, and it's increasing steadily to some level. And well, at this point, you can or you cannot guess whether it's going to be bounded above or not, because it could go like a log function forever. So let's make it a little bit bigger, not to 11, not to 10, but to 100. Okay, that's quite big. So if you draw the graph of a sequence from A1 to A100, then you can see that it's leveling off, like flatten out. So you can see that it's not gonna go infinite. If you're not convinced yet, you can still make it a bigger, like to the 1,000. Okay, we've made 1,000, up to 1,000 entries, and still not converging and going into infinite. So now you can convince that it's not going to happen. It's always going to be bounded above. It doesn't have to have a fixed bound. Like it's definitely all the entries are less than 3. So it has a bound above all the entry. And it's increasing. We checked it, right? So what can conclude here? The sequence an defined in this way is convergent. We can prove it. I mean, we just show you the evidence that this should be convergent because of the theorem. We didn't prove it. How can we prove it? Hmm? Yeah, well, I mean, that, okay. So the limit, I didn't introduce this notation yet, but the limit equals to some natural number. This is the fact, and this fact is coming from this theorem. Yes. So we decided to call whatever the limit of the sequence to be E, the natural constant. Well, how do you prove it? You first show that this sequence is monotonic increasing, showing that an is always less than an plus 1. And then second, this is bounded below, I rounded above, that every entry of the sequence is actually less than 3. So there's a proof in the book, so you can always go to the book to find out how it proved. Now, I want to talk about a technical definition of the limit. Let me define another definition, actually not different from the previous one, of the convergence of a sequence. Oh, that's it. All right, so here a sequence AN is said to be convergent to L if the following statement is true for, so I'm going to quote the following statement because it has a name and it's very important in understanding of convergence of a function later. Every epsilon, which is positive, there exists n, which is natural number, large natural number usually, such that an minus L absolute value is less than epsilon for any n bigger than or equal to n. So I think some of you already have seen it or heard about this definition. It's called epsilon delta statement. And I don't want to scare you by this statement, or I don't want to make you like think like a mathematician, but I just want you to know that this is very commonsensical definition. You will understand that there's no way you can actually conceive what is about the limit, what is about conversion, what happens to the limit. So think about this case. This is talking about the difference between the sequence and some number. So in other words, it's actually an error. Let's say I want to estimate my limit by the sequence an. So this thing, the absolute value of difference, measures you how much error you have by estimating the number L by the sequence an. So here is the example. Everyone knows that there is 1 plus 1 over n to the power of n is e, which is 2.718, something like this, right? Now, this is not a rational number. The decimal point goes infinite. But you also want precise value, as precise as possible. It's impossible to get exactly precise number, but you just want to have more than 3 decimal, right? Then what do? You just plug in large n, right? So the question is, if, let's say, I want to be precise up to 3 decimal point, how large my n should be? So if I have 100, 1 plus. So instead of n, let's say I replaced n by 100, then I get some number, maybe 2.7 something, but maybe different from the second decimal point. So it's not really accurate. So I just want to know if my estimate is as accurate as up to 3 decimal point, I need to know how big my n must be. That's the question. So this definition, what does it tell you? If you want up to some accuracy or up to some error rate or error estimate, then there is definitely a number n that guarantees that estimate is accurate up to this accuracy here. So I would call it this as a precision here. Precision. So if you have a magnifying glass or you have a microscope, then you have a certain precision. Like if you, what does the precision means? Precision means that up to certain level, you cannot distinguish 2 points which differently, right? So in that sense, you can have no other choice but having these 2 points actually be the same point, right? So if you have a precision like epsilon to be 0.00, let's say 0.1 or something, then you can say that your estimate an of the limit is at least as accurate up to 3 decimal point, right? So it could be up to 4th decimal point, but let's be safe. Let's say up to 3 decimal points, your estimate is accurate. But this statement, the definition, ensures that in order to get that precision, how much your index should be, how large should your index be. That's the definition of convergence. If you know that estimate of your index that ensures your precision, whatever the precision is, however small your precision is, if you certainly know how large your index should be in order to get the accurate value of your limit, then you can safely say this must converge. There's no other choice, right? That's the meaning of our convergence. That's the meaning of epsilon delta. But let's see. Let me give a precise how this definition is precisely used in proving some of the convergence. So for example, let's say I have a sequence an equals to 1 over n. Everyone knows that it equals to 0. Well, maybe there are many ways to prove it or convince you, because 1 over n gets smaller and smaller, but doesn't get smaller than 0, so S3 goes to 0. But let's prove it. Well, you kind of intuitively know that it must be 0, but unless you prove it, you never know it's true. So how do you prove it? So it says, for every epsilon, I need to know such n. So let's plug in some epsilon here. So if epsilon is 1 over 10, which is 0.1, which means that I want to estimate my limit 0 by 1 over n by making n large, how large this n should be. Then let's say, let n, large n, should be 11. What does this imply? Being n equals to 11 implies that if n is larger or equal to n, which is 11, what happens? The difference between the entry of the sequence 1 over n and the limit, which is simply 1 over n again, is, so it's at least bigger than 1 over 11, right? Because n is bigger than 11. Smaller than 11, 1 over 11, right? So 1 over 11 is smaller than 1 over 10, which is epsilon, right? So if I given with the epsilon 1 over 10, then I know that I can just take n equals to 11. That makes this inequality true for every n bigger than large n. So let's change a little bit. So instead of 10, let's make it 100. So my epsilon is 0.01. Then how large should my n be? Large n should be, yeah, 101. So then if I take n, small n, bigger than or equal to 101, then this difference, so this is the error difference. So error between actual limit and the sequence being smaller than 1 over 101, and it's smaller than 1 over 100, which is epsilon. So that's true. So now you have a pattern here, right? So you can safely say from this point, however your epsilon is small, let's say it's as small as 10 to the what? 10 to the minus m here. No matter how large m is, you can always take n to be 10 to the power of m plus 1, so that this all makes sense, right? Okay, well, what if I don't get this epsilon as in form of 10 to the minus m? Okay, so then what do? Let's say epsilon is very small. What do we do? So let's say epsilon is smaller than 1. So then I get n to be some integer, which is 1 bigger than the largest integer smaller than 1 over epsilon. So this is the Gaussian Gauss notation here. So this means that the largest integer among smaller than 1 over epsilon. So just take the largest as possible, but not exceeding 1 over epsilon. And then plus 1 for safety. And then what happens? If n is bigger than n, then 1 over n is certainly less than 1 over large n, and 1 over large n is certainly less than epsilon, because you chose that way. So it's really not practical to prove the limit, but it's practical to know what's happening here. What's the meaning of the definition here? This is so simple that you don't really need the computation to compute what is 0. But let's say like this situation, if you really want to compute the actual value of the limit, you really want to know how large your index should be in the sequence. So that is guaranteed in the definition, and sometimes the way to find the precision is encoded into the proof of that convergence of the sequence according to that definitions. Right, so you can see the book in the chapter 1, I included sequence and series and the computation of functions. The reason why I mentioned the sequence is not only just giving a glimpse of what's happening in the sequence or the convergence of a function or a continuity of a function, but also I want to talk about the basic functions like exponential function, sine function, and cosine function. So these functions are so basic, so primitive that everyone knows what that is, but when it comes to the actual computation, nobody knows how to compute unless they use the calculator. But our goal is to make a calculator of our own. We're not going to use the calculator, we're going to make a calculator as if we don't have any calculator in this world. So how do we compute exponential? We need to use a kind of notion of convergence because it heavily depends on the convergence of a series. And so is sine and cosine. So therefore, I'm talking about the sequence here. And the next time, I'm going to finish up the sequence part and then move on to the series part. So before we finish, if you have any questions, let me know after we dismiss. And also, if you want to know, just look at the book briefly, then here's the book. Take your time to read the book here. And see you on Wednesday.